Hey, so I'm Dr. Jeff Mahler. I am the robot arm guy, robot arm grasping guy. I think that was alluded to in the previous talk. So I'll be talking to you today about a project that was the backbone of my PhD research called the Dexterity Network, which is about teaching robots how to grasp a wide variety of objects using simulation to reality transfer learning. And I'll talk a little bit about the end about what we're doing at the startup, but mostly we'll focus on research. So I was requested by Michael to say a little bit about what we do in the lab, Professor Ken Goldberg's lab at UC Berkeley. We're a big robotics lab consisting of about 8 PhDs, 20 or more undergrads. So we have a lot of talent. We mostly focus on applications of machine learning to robotics. So how can we get robots to do useful tasks for people, such as making a bed or grasping objects in logistics, or even assisting with surgery, as opposed to thinking necessarily about the high-level algorithms. Although we do think a lot about the algorithms as well, we're very focused on applications. And a big theme that I think connects to this particular showcase is the idea of cloud robotics, or now as we're thinking of it, fog robotics. Thinking about how robots can share data and we can have algorithms and applications that transfer between robots while actually preserving the integrity and security of data. So not sharing all data everywhere in the cloud that everyone could use it, but thinking about trade-offs where we can learn certain models from all the data we have available from robots and fine-tune them to specific applications in this gateway layer, which we're calling the fog. And so just a little teaser of what we work on in the lab. One problem is in applications in assistive robotics. So this is one project that was in robotic bed making, having a robot actually pull sheets over a bed in order to make it from an unstructured initial condition. Another big research area in the lab is in computer vision. We think about how to train robots to recognize different objects and also segment out different objects from unstructured images like this into the individual components, so that robots could know, for example, to give you the watermelon from the scene. They know which pixels correspond to the watermelon and where to grab them. And which leads me into the next thing, robot dexterity or robot grasping, which is what I focus a lot of my own research on, which was recognized by Bill Gates as one of the top 10 breakthrough technologies of 2019. Our work was recognized here. So why is this problem so hard? Of course, it has tremendous applications. The ability to rapidly and reliably grasp a wide variety of objects could benefit applications in e-commerce or fulfillment, handling the growing number of products that are coming on the market in places like Amazon. Handling new flexible automation lines, being able to set up new manufacturing with new parts rapidly, not having to hard code exactly where the robot has to move every time. Can we have robots adapt, say, to 3D printed parts? And of course, long term, we're interested in how robots could assist in the home, augmenting a system like bed making to perhaps clean up your kitchen and dealing with objects in very unstructured settings such as this. But nonetheless, today, even very simple manipulation tasks, or so we think as humans, are very difficult for robots. So in order fulfillment, tasks such as this, where people are moving individual items from essentially one container into another, is still done almost entirely manually, and people are spending over $10 billion on this problem a year. And Rodney Brooks, one of the big leaders of thought leaders in robotics, also co-founder of Rethink, named this as a grand challenge for robotics, the ability to grasp millions of different sizes and shaped objects. So one of the things that makes it particularly hard is perception, dealing with sensor data and breaking that into components. I showed segmentation earlier. What's challenging is that robots don't have a lot of prior knowledge baked into them already. They start with a raw image such as this, and then if they need to figure out, for example, which pixels belong to which objects, and furthermore, where to grab those objects, it becomes very challenging when you have high exposure, so you see these white areas. In addition, we often use geometric data such as depth images, and you can see it's very blurred out, there's holes in the image. So it's very difficult for a robot to infer the precise shape and position of different objects in the scene. So a research trend that has gotten a lot of traction beyond just robotics is to use deep learning for these kind of image analysis problems. Using deep neural networks that can essentially apply a series of filters to an image that are learned over tremendous amounts of data to recognize, for example, whether or not an image contains a car, where the car is in an image, and there's been tremendous progress in computer vision. We've also seen progress in games. AlphaGo, for example, beating Lee in the big televised event a few years back. And then in natural language, in machine translation in particular, there have been really surprising results. The one thing that is common to these problems that is more challenging in robotics is that there is a source of data already available. In computer vision, people have spent a long time, actually decades, curating large data sets of labeled images that can be learned on. In games, you have a simulation environment where you can essentially launch it on the cloud or something like this and run continuously and get data that is reflecting to some extent what real outcomes of the games look like. And in natural language, they've similarly been curating massive data sets. So a big challenge in robotics was thinking about where we can get that data, not necessarily even how to make fancier algorithms, but just how can we get large amounts of data. One possibility is in human labeling. So having humans take images and label bounded regions of the image where a robot should place its hand in order to successfully grasp objects. A second idea that has been very popular is called self-supervision, where the robot can attempt many grasps over time and reset itself and sort of self-learn. One of the challenges, though, with both of these methods is that it takes many months or even years to collect on the order of millions of data points, which is about the order of magnitude that's been recognized as being needed to get compelling results on these problems. And similarly, there's an asymptote of learning. So getting to 1 million data points, you can get from 0 to 80% success in grasping, but getting from 1 million to 10 million data points will only get another, say, 10% up to 90% grasping success. So getting beyond to 100 million data points, it's not clear how to extend these methods, especially because you need to relabel a new data set for every new hardware system, every new robot arm, camera, and type of hand the robot has. So where my research started was looking at how we can actually use simulation and essentially turn grasping into something like a game that was used to train some of the game playing system before. In particular, looking at equations or physical models that can be used to predict the success of grasps from some sort of geometric model of the object, such as a 3D mesh model. And we went back and looked at actually a bunch of the research that had been done previously and found that this is actually the majority of grasping research, looking at how to measure success of a grasp through the ability of a hand to bound an object, to keep it in a static equilibrium, or to keep it dynamically stable in the presence of perturbation, something trying to knock an object out of the robot's hand. And so the dexterity network is essentially a way to use these equations to train deep neural networks automatically. So in particular, we collected a large data set of meshes and used that to synthesize millions of different images and corresponding locations of these images where successful grasping location would be for the robot, and use that to train custom vision models for different hardware systems to enable robots to generalize to new objects. So now I'll talk a little bit about how that works. The first stage in the process is what we call synthetic data set generation. So this is actually generating the data that the robot's going to learn from. We start with the set of 3D CAD models. And then for each CAD model, we actually will drop them into a random configuration, say in a bin. Or you could also imagine placing these CAD models virtually onto shelves, for example, or even on a tabletop. And then what we can do is, because we know where all these CAD models are, we can look at locations on those models where the robot's hand might grab and evaluate them using equations to determine the success or failure of a grasp. And so we can do that. Here on the right, it's showing a number of alternative grasps evaluated for a single model. On the top, parallel jaws, on the bottom, suction. And to say a little bit more about that, one of the things we had to develop in this project was a new model of contact for the parallel jaw gripping system, so 2 fingers pinching to grab an object, and suction cup grippers that can use vacuum to essentially hold the object in place with a compliant cup such as this. So in particular, we looked at how to model both the ability of this to apply forces and torques to the object through contact, and also the robustness of grasping positions to uncertainty. So many times in reality, if a robot goes to attempt a grasp, it may not reach exactly where it wanted to go because of imprecision in the robot arm. So we can model that stochastically. And using these models, we can take individual CAD models and score essentially different grasping locations for an individual model. So here on the left, you're seeing each line is corresponding to a particular pinch of the object, and the red to green is showing essentially bad to good grasping points in the object. So you can use these models to, say, grasp sort of opposite facing surfaces near the center of mass of the object. That's something that's good for the pinching or parallel jaw gripper. And on the suction cup, I'll run this one more time, the points that are on flat surfaces near the center of mass tend to be good. But rather than sort of hard coding that knowledge in there, we can evaluate the ability, for example, of the gripper to resist gravity or other perturbations on the object. Now, to get generalization, we need to introduce some diversity into the learning process. So one of the things that we did in the DexNet project was to go to the 3D model data sets on the web that are starting to be available due to 3D printing. We're seeing this massive growth trend around the start of 2010, this decade. And we were able to pull over 10,000 3D models from various sources, including things people made for games, things from 3D printing, and scan models. And then we built a system in collaboration with Google to actually distribute computation of grasp across these models by giving sort of subsets of models to different workers and aggregating all the data back, allowing us to do very large-scale analysis of grasping positions on the object. So then how can we actually use that to teach a robot to grasp based on images? That's what we ultimately like to do here. Well, one of the things we noted is that we can actually use a system like this to train a detector for recognizing locations that look like good grasping locations. The way we do that is we put CAD models in virtual configurations, such as in the bin, and then render virtual images of the objects in the bin. And then we can center little thumbnails of the object on the good and bad grasping location. So up here you see, here's one example of a good pinch grasp viewed from an overhead camera on this random object. And similarly, suction grasp here. We also include a large number of negative examples showing the robot where bad grasping locations are so it knows to avoid those. For example, suctioning on the corner or non-flat surfaces of objects. And once we have this image data set, we now essentially have images plus success and failure labels, an image classification problem, and now we can repurpose some of the ideas from computer vision to train a system to detect grasps directly from these depth images. Well, one thing we did was develop our own architecture to support actual grasping. So we took a convolutional neural network and augmented it to not only include just the image, but also the grasping coordinates, the center pixels, and the angle approach in the image space. To deploy this on a real system, we need to find a way to use this neural network to actually analyze images and choose the best grasp. So in the past slide, I described how we could learn to detect whether or not a grasp was good or bad. Now we want to understand what's the best. We essentially deploy these neural networks in what's called a policy that searches over the image for what has the maximum probability of success. So what's classified as most likely to be a successful grasp in the image space. And we can actually do this for multiple types of hands. That was one of the cool things we found in the past year was we can train sort of separate brains for each hand that the robot has and use them separately on the robot to rank between two different types of hands that the robot has. So we have a suction cup here, a parallel jaw gripper here, and the robot can automatically compare the outputs of these two systems to decide where to pinch and extract just one object from a cluttered scene. I guess the video is not working, unfortunately. Is it coming up? Well, so this is, oh, here we go. So now this is showing the method I described deployed on the real robot. So what it's doing is iteratively taking an image of the scene with a depth camera that's measuring the geometry, then analyzing the scene to rank to find the most successful grasp or what's predicted to be most successful, and then attempting that grasp to extract one object. So here what you're seeing is the robot can actually fail and learn how to recover from that and remember when it failed and attempt to use the other hand. It's able to generalize to a diverse set of objects, and it's able to use the different grippers not only for different objects, but different objects in different positions and orientations. So when it's easier to use the suction cup, it'll often do that. We find it uses about 80% of the time. But in some cases, such as these challenging objects with odd geometries, it'll more often use the pinchers, which can handle some of these strange geometric features of objects. This appeared in Science Robotics at the beginning of this year, so I encourage you to check that out. It's got a detailed summary of this work on the Dexterity Network. This problem is by no means solved, so what we've been able to do is essentially show that if you have a constrained setting and you know enough about the hardware system, you can train a neural network about 100x faster than if a robot was collecting data on its own. But nonetheless, there's still failure modes and there's room for improvement. One thing we're thinking about is whether or not performance can be improved with real data. So as the robot goes out there in the wild and starts collecting data, how can it learn the fastest to adapt to the failures it gets? For example, the simulation may not be perfect. It may be making some mistakes. The robot needs to unlearn certain things that it might have learned in the past based on this data. A second thing we're thinking about is whether or not this method can be extended to other sort of tasks that the robot will do. For example, packing items. It's not, in a lot of cases, enough to just pick an item, but you actually need to place it somewhere. For example, in a shelf, in a drawer, or into boxes. So we're looking at applications to these sort of manipulation primitives. And we're also looking at how this could be used in commercial application. And so that's where I started a new startup called Ambidextrous. We're looking at how to use technology such as this to rapidly train robots to pick a diversity of products in e-commerce applications, particularly looking at order fulfillment, where a lot of items are being handled one by one manually in warehouses today. And I can't say too much about this here, but I'd love to talk more offline. I'd like to thank research sponsors. This is a long effort, over 5 years of research, as well as a number of collaborators, so big thanks to them. And I'd love to take any questions that you might have.
Dr. Mahler, you know, I want to respect your privacy and stuff, but can you talk about maybe the future of Ambidextrous, the company, and what would be some of your initial things you'd like to do, some of the initial deliverables? I mean, would you at some point, for example, be seeking capital and deploying this, or pursue a licensing model to Siemens and Cisco and some of the other names that were up on
Sure.
slide?
Yeah, I can say a little bit more. So so we just closed a round of pre-seed funding, and what we're looking to do in the next year is develop the technology towards specific applications in the logistics space. One application of interest is called piece picking. That's what I've been alluding to in e-commerce. It's basically handling individual items and moving them from point A to point B. Some other applications where we see interest are in industrial kitting, sortation of mail. That's a big problem for robotic manipulation. Sortation of recyclables. That's actually a massive problem now, especially that a lot of recycling is not being sold away. Figuring out where to move it and what to do with those items. As well as we've received interest from other things such as service robots. I think there's going to be some up and coming opportunities in things like pharmacies and assistive care centers where robots can be in constrained settings retrieving, say, medications for people at scheduled times a day. The company itself, we're looking to license the technology, but we're still developing our product, and I can't say too much about it yet.
Thank you.
Yes.
I'm wondering, have you tried anything more than just the vacuum and the pincher?
Yes, so we've also tried soft hands to some extent.
Like that?
Yeah. Yes, so there's pneumatic hands that essentially will inflate and close like this. So a lot of them have 2 fingers.
Yeah.
We can handle those to some extent, but one thing that's difficult is the numbers of degrees of freedom that those hands have. So multi-fingered hands also have this problem. If you've seen, there's a big press announcement from OpenAI on a cube rotating hand. Those hands can be harder to deal with because of how many ways you can move the hand and how hard it is to precisely move it to those positions. So what we typically do with those kind of hands is restrict them in some way. Say you can only close in like a power grasp like this. You're not able to sort of do complex rotations of the fingers and so on.
Yeah, because I saw in the video, like most of the objects you use are like pretty small. So I would say like it probably works better with like a vacuum. But
Yes.
like let's say for e-commerce or Amazon, for example, a lot of the objects are quite large. I'm assuming in that case the vacuum may not be the best.
Right. There's different grippers for different problems, and that's one of the interesting things about this field right now is the human-centric perspective is that we have one hand that can sort of do everything, but on the robot side, it's really not like that. There's, the pincher grippers are often used in manufacturing. They're nice for assembly, and they're simple. They don't break that easily. Suction cups are used in a lot of material handling applications, handling products in e-commerce, but also just moving boxes around. And then now in food handling robots, these soft grippers are becoming more and more common. They don't damage objects that easily, for example. So we're looking to expand the set of grippers and kind of understand where the best opportunities are to handle a wider variety of objects. Yes?
I've heard of kindred AI doing something similar to this, and so I was wondering what's differentiating here from their training and picking objects.
Yeah, so Kindred's doing some cool stuff. They have a sortation system for moving objects into essentially different cubbies, sorting out orders. Their system, to the best of my knowledge, is working based on human teaching. What we're looking at is applications where there's a need to rapidly apply a new gripping system to a wide variety of objects without having to have a human in the loop for training.
Can you touch on, Dr. Mahler, can you touch on a couple of the other areas of the auto lab?
Sure. I'm happy to dig in a little more. One that I didn't mention is in robotic surgery, or at least I mentioned only very briefly. So Professor Goldberg's been working for, I think, 15 or more years on the problem of robot-assisted surgery, where robots can be used as essentially another tool in a surgeon's toolkit. So today there's Da Vinci systems where a surgeon will teleoperate and tell the robot exactly where to go in a surgical setting. Our research is basically trying to lift the control a little bit higher level and give the robot ability to do certain subtasks, such as tying a suture. If a surgeon was able to grab two ends of the suture, can the robot do the little knot autonomously and remove some of those tedious manipulation tasks for the surgeon? To say a little bit more about other projects, the bed making project I showed briefly, there's a big trend to look more now at deformable object manipulation. So we're looking at ways to simulate deformable objects, do something similar to DexNet, and think about how to fold them and stretch them to cover different surfaces. Yes?
Have you considered agriculture and farming?
Yes, I'm glad you mentioned that actually. Professor Goldberg is looking at that, in particular in irrigation. So how robots can help deliver specific amounts of water to specific plants out there in the field. They're looking at mobile robot applications where robots drive around and based on satellite imagery understand where to go and provide care to the different plants out there in the field. On the grasping side, we thought a little bit about like fruit picking. I think that's a very interesting problem. I don't know too much about it, but one of the challenges there is definitely that the objects are attached to something, so you need to pick them and not damage them, which requires a little bit of extra thought on top of just picking an object when it's by itself and moving it. You need to sort of break it away in a clean manner. Yes?
So besides the pinch points of the shapes you mentioned, have you ever considered factors called the material of the softness of the object, and as well as if an object is blocked by another object, how do you
Yeah, that's a great question. So in terms of the material softness, we have an active research project on that, looking at how the robot can find the right trade-off in terms of leveraging the fact that a material is soft to sort of get a better pinch on it without damaging the object. And we're thinking about how to formalize that sort of trade-off. In terms of blocking the objects, that's an interesting problem because that's something we can model fairly well by looking at the contacts between objects. So that's another thing we're thinking about, is how to bake that into the models. Essentially, one of the ways we measure success is to see whether or not, if the robot establishes contact with an object, can it resist all the forces and torques that are likely to occur on that object. So if we can look at the contacts between objects, we can know, for example, this object's pressing on here. I need to be able to pull it this way, but not necessarily this way against the other object, and understand those sort of geometric features of the problem. Yes?
Are you using any sensing at the end effector, or is there soft vision?
So this is all vision at this point, and it's what we call open loop. So the robot finds a point and then just goes there. But certainly end-of-hand sensing is valuable in this problem. One of the challenges is that tactile sensors are not as mature. So there's a lot of new interesting research going on. The gel site sensor is one thing that I'm excited about but haven't used. One way in which it could be used is to have the robot quickly recover or adapt grasps on the fly based on where it finds a contacts object.
So if it's open loop, the robot doesn't know if it was successful.
Yeah, it only knows based on additional sensors. So what we often use in these experiments is actually load cells. So it's measuring the weight of this bin on the bottom to understand success and failures. We usually also in experiments are hand labeling this data so that way we have some sort of ground truth. Yes.
Well, this is kind of a crazy question, but do you anticipate backlash from like labor groups at some point in the future about, you know, the perfecting the use of robotics to do various things that are some would consider manual labor?
Mm-hmm. Yeah, I think I do anticipate that being a problem. I think part of or one way to sort of mitigate that is in how we communicate these new technologies, because I don't see I see these as really being tools that people can use. Like, people are not going to be removed from the warehouse, but what they may not be doing is handling the individual objects anymore. What they may be doing instead is handling exceptions or providing batches of objects that are then handled by robots. So I see this not as artificial intelligence that's going to take over all human tasks, but another tool in the warehouse, another technology like a forklift or something like that that augments humans and enables us to make warehouses that much more dense, that much more efficient.
That still doesn't really answer the question in a way, because by apparently making people more efficient, you have fewer employees that you need. So, yeah,
right.
Thinking a little bit beyond that.
Right. Yeah, I think that's a good point. I just think there's a lot of fear about AI and robotics in particular. That is partially due to messaging about AI singularity, perhaps to some extent, rather than, I think since the Industrial Revolution, maybe much earlier than that, these things have been happening. For example, farming used to be like the majority of human labor force, and now it's a very small percentage of what we do. So I think communicating that and finding ways in which we can put human labor to new jobs is going to be a big piece of the puzzle. Yeah.
So I'm just curious, for the neural net training, are you sending data live as it is sorting, or is it like a two-step process? You're collecting the data locally and then pushing it off to the cloud to do the training?
So what we do here is we collect it locally and then push it to do the training from time to time. You can also train on the fly. So our research method is more about simulation aspects of the problem. So training offline, then giving it to the robot. But online, you can use a number of different techniques to learn.
And what are the constraints of the robot? There's a very specific robot with its payload capability and envelope. So, is there a particular reason for this specific robot, and what are some of the constraints you have to sort of deal with?
That's a great question. We chose this robot largely because it's human safe. This particular robot, it can't really hurt you. It moves fast, but it's got a very low payload, so that's one of the reasons we're using small objects here. You can get in the way and it's okay. But one of the big constraints that comes up with different robots is the kinematics or the geometry of the arm. That does affect the problem a lot, and that's something I didn't talk about here today, but when the robot goes to grab something, where does it put its elbow, for example? When it's grabbing out of complex places like shelves or digging in bins that are very deep, it has to think about those challenges as well. So what we've tried to do on the research side is sort of abstract that away and lift it away from the problem to some extent. The robot, you can see, is always keeping its elbows up.
So you have that constraint programmed in that it
Yes.
won't go beyond those ranges, and that would define the size of that bin.
Yes.
Thank you, Dr.
Yeah,
Wells.
thank you.
Great.